If you're a JavaScript developer, you've probably typed Math.random thousands of times without a second thought. But behind that simple, everyday function is a pretty wild story and a hidden flaw that took years to find and fix.
I mean, think about it. We use it for everything, right? From shuffling a playlist to creating particle effects in a game. We just trust it to be random. But is it, really? The answer, it turns out, is way more complicated than you'd think.
So, to get to the bottom of this, we first have to wrap our heads around a fundamental truth. Computers are predictable. They're designed to follow instructions perfectly, which is kind of the exact opposite of being random. So, to create randomness, they have to use a very clever illusion.
And that illusion is called a pseudo-random number generator, or PRNG. The key word here is pseudo. It's an algorithm that just spits out a long sequence of numbers that looks random to us humans. But here's the trick. That entire sequence is determined by a single starting number, called a seed. If you use the same seed, you get the exact same random numbers in the exact same order, every single time.
A classic example of this is the linear congruential generator. Now, don't worry about memorizing the formula, just get the idea. You take a number, you do some simple multiplication and addition, and that gives you the next number. Then you take that number and do it all over again. It's a simple, predictable loop that's designed to create a chaotic, unpredictable-looking result.
For a long time, the Math.random function in Chrome's V8 engine, the engine that powers a huge chunk of the web, it used an algorithm built on this kind of simple, fast idea. But as it turned out, that speed came at a pretty steep cost. The algorithm was fundamentally flawed.
The algorithm was called MWC1616, and up until late 2015, this was the little engine behind Math.random for millions and millions of us. It was chosen because it was incredibly fast and didn't use much memory. But hiding just beneath that efficient surface, there were some serious cracks in its foundation.
So what were these cracks? Well, for starters, its state size was just 64 bits. Think of this as its memory or its creative potential. It just wasn't enough to generate real complexity. This meant it had a short period. The sequence of numbers could start repeating itself in under 40 million tries. Now, 40 million sounds like a lot, but for a computer, that's nothing. It's dangerously short. And worst of all, it failed a whole bunch of standard statistical tests designed to spot exactly this kind of bad randomness.
And V8's problem wasn't some one-off thing. The history of computer science is absolutely littered with flawed generators. The most notorious was an algorithm called Randu, which was used in serious scientific research for years before someone realized it was deeply, deeply biased. The discovery threw the results of countless studies into question. A powerful reminder that the quality of your random numbers really, really matters.
But how can you actually prove a generator is bad? I mean, you can't just look at a list of numbers and go, yep, that looks wrong. You need to put it to the test. You need an independent and, frankly, a notoriously tough referee. And in the world of random number generation, that referee is called Test U01. It's a software library from the University of Montreal, and it is the absolute gold standard. It doesn't just run one or two tests. It runs a brutal mathematical gauntlet of statistical analyses, all designed to hunt for the slightest hint of a hidden pattern or flaw. A famous quote from the mathematician George Marsegaglia perfectly captures the problem with weak generators like V8's old MWC1616. It sounds a little poetic, but it points to a surprisingly visual flaw. So what does that even mean? Simply put, the random numbers aren't actually independent from each other. If you take, say, 3 numbers in a row and use them as x, y, and z coordinates to plot a point in 3D space, a good generator should create a random, shapeless cloud. But a weak one, it reveals a hidden structure. The points all fall onto a small number of predictable parallel planes. It's like seeing the ghost of the algorithm in the machine. And this is exactly the kind of weakness Test U01 is built to find. The old Math.random failed specific tests like matrix rank and linear comp, tests designed to detect these hidden linear patterns. The math was undeniable, the randomness was just low quality.
So the V8 team needed a replacement, and fast. They had to find an algorithm that was still super quick, but could also stand up to the intense scrutiny of modern statistical tests.
They found their solution in an algorithm called ExerShift 128+. And it was so good, it wasn't just adopted by Chrome's V8 engine. Firefox and Safari also switched over, basically making it the new standard for Math.random across the entire modern web.
The first and most obvious upgrade was the state size. It doubled from 64 to 128 bits. Now, that might not sound like a huge leap, but because we're talking about exponents, it doesn't just double the complexity, it increases it by a factor of, well, billions. It makes the generator's internal state vastly more difficult to predict.
And what does a 128-bit state get you in the real world? It gets you a period length of 2 to the power of 128 minus 1. This number is so astronomically large that the sequence of numbers will not repeat itself until long, long after our sun has burned out. For all practical purposes, it's infinite.
I mean, the difference is just stark when you see them side by side. The new algorithm has a bigger state, a vastly longer period, and most importantly, it passes Big Crush, the absolute toughest battery of tests that TestU01 has. It's a decisive mathematical victory.
So, problem solved. The new Math.random is fast, it's high quality, it's reliable. But it comes with one really critical warning that every single developer needs to understand. Even with all of these fantastic improvements, Math.random is not cryptographically secure. And the reason is simple. It's still predictable. An attacker who can figure out its 128-bit internal state, which is hard but not impossible, can then predict every single random number the function will ever generate.
This makes it the perfect tool for most things. You know, generative art, video game physics, shuffling an array, but it also means you must never, ever use it for anything where unpredictability is a security requirement. So, no generating session tokens, no encryption keys, no password reset links. Just don't.
For those high-stakes jobs, you need to reach for a different tool entirely. The Web Cryptography API, specifically window.crypto.getRandomValues. This is designed from the ground up for security. It doesn't just run an algorithm. It actually taps into the operating system's own sources of entropy, things like tiny variations in your mouse movements and network timing to generate truly unpredictable values.
The whole story of Math.random is just a perfect example of how our simplest tools are often built on decades of research, arguments, and brilliant engineering. It's this hidden world of complexity, right below the surface of the code we write every day. And it really makes you wonder, what other everyday functions have a story like this one to tell?